Thank you for coming to the Meetup today. I'm going to be talking and sharing with you about the TiDB query optimization. And let's go from there. Okay, so my name is Ahmad Ghazal. I'm a database architect at PingCAP. And PingCAP is the company behind TiDB. So we'll talk about TiDB is the product, PingCAP is the company name. And I'm an optimizer architect, database architect, but mostly working in optimizations. I worked at Teradata, Oracle, Huawei MPPDB, Meta, and most recently at TiDB. I have 20 plus US patents in this area. And I'm a co-founder of Big Bench. So Big Bench is one of the standard benchmarks in the database by the TPC. So that's one of the key areas that I would like to talk about here. I'm mentioning my colleague Terry because I stole his slides. He did a webinar on this. And if you see some nice looking slides, that's his. If you see something that doesn't look so nice, that's probably mine. And Terry, he has similar background. He worked for DB2 most of his career as an optimizer. MariaDB recently before joining PingCAP. And he has lots of patents, 45 plus US patents. Yes. Okay, so before I talk about query optimizations overall, I'm going to talk about query optimizations in TiDB. So let me just motivate a little bit by some customer stories. Just to talk about the size of the data and what TiDB can do. So this is something that came from one of TiDB customers who said things publicly. So this is kind of public information they talked about. So Flipkart is an e-commerce in India, I think one of the biggest, probably the biggest. So they are a TiDB user, and they have massive applications. And with TiDB, they have accomplished huge performance from these numbers you can see here. Number of reads and writes. So in databases, you always talk about reads and writes, right? And you worry about performance of both. And the size of the data itself has been reduced tremendously by 82% with using TiDB. So this one is, I believe, was a MySQL customer. So that's one example of how people are using TiDB. The other one is Pinterest. I'm sure you guys are familiar with that. That's also in their own words. So prior to TiDB, they were worried about the scale. How their data is going to grow in the next 3 to 5 years, and how they can scale that. And with TiDB, they have 3x to 5x performance latency reduction, and some more details on the 99% and the 95%, which I don't want to bother you with some of these details, but it's a huge performance improvement. One thing interesting here is for those who are understand transactions, there are different level of transaction semantics. TiDB has high standard for transactions, which is read after write consistency, and this is very important in the transaction system because when you write data, you want the data to be available to the user as soon as possible. And with TiDB also we have a row store and a column store. So you need the data to be available as soon as possible when it goes from the row store to the column store itself. Pinterest, they have accomplished a simpler architecture with TiDB than before. Okay, so 2 customers, and there are a lot who have shared their stories. And if you're interested, I can share the slides. You can look at these blogs. You have tons of cases here. Okay, so let's move into the technical content here. Okay, so I suppose all of you guys are familiar with databases, familiar with SQL. So some of the things I'm gonna talk about SQL, I'm gonna make assumptions that people know about SQL. Sorry about that. And if something doesn't make sense, let me know. So, you know, Ted Codd, he's an inventor of the relational database management systems. And he's also behind this, the SQL language. And the most powerful thing about SQL is that it is declarative. So it allows developer to say what they want. They don't have to say how to find it. So this is versus procedural. So when you write a C, C++ code, you have to say exactly how you're doing the computation, right? So you have to do the how and in addition to the what, right? With SQL, you just say, I want to join these two tables, I want to retrieve this information, and I'm going to leave it to the database to figure out how to do it. So that's the most powerful thing about SQL. It just makes it easier for developers to interact with the database. Make sense? Okay. So because of the declarativeness in the SQL, and TiDB is a SQL database, like 80% of databases out there are SQL based. There are NoSQL. I'm sure you heard about NoSQL databases. So we're not a NoSQL database. We are a SQL database. We are MySQL compatible. And because of we have to do the how part for the SQL, we have something called, query optimizations. And this is maybe to summarize what a query optimizer do in plain English in a very high level. And I think you could say this is really oversimplified, but this needs to be simplified so that it makes sense for, in a presentation like this. So when we talk about a query optimizer, I mean, maybe taking a step back, users submit SQL and they get results, right? They say select star from table 1 and they get all the data for table 1. So usually things work like there is a parser that parses the query and check if it is correct and incorrect and builds a parse tree. And then the next step is the planner or optimizer. People use these names interchangeably. So this is what the optimizer do beyond the parsing here. So the components of the optimizations or the optimizer is that there is a rewrite. So it takes a SQL, this declarative SQL, try to convert it to another SQL that's more efficient. And I'll give you some examples here. And after that, there is this trying to build the execution plan. And that's first done by this logical enumeration. So logical enumeration means that the optimizer will look at different ways of executing the query. So in a database, there are different ways you can access the data. There are different ways you could join data. There are different ways you could aggregate the data, right? And making the right choices is very critical to the performance of the execution of that query. Okay, so that's what logical enumeration means here. The most common thing about enumeration is the join order. So you understand SQL and joins, right? You could be joining 5 tables, and you could do the join order in different ways. So if all the tables are connected to each other, you're talking about 5 factorial possible ways, right? So after this enumeration, after all the feasible plans have been identified, then the next step is to find out how you're going to produce the execution plan. So, in databases there are, and as I said, there are different. So join is a logical operator. Merge join is a physical operator. So if you're familiar with merge joins, hash joins, there is index joins. So these are different ways to execute physically what's a join in a database, right? So that's the next step, is to find out which of these physical operators is the best choice. And it really depends on the data distribution. It depends on the statistics of the underlying data and so many other factors, right? So that's the next step. And then eventually the optimizer will provide an execution plan, and supposedly to be the best execution plan. And then that plan will be taken to the next stage, which is what's called the execution engine, which will actually do the execution, produce the results, give it back to the user. Okay, so I mentioned 3 things here, right? So rewrite, logical enumeration, logical to physical. So let me give an example. So this is a very simple example of a rewrite. So here you have a query that joins 2 tables, T1 and T2. The join predicate is A1 equal A2, and there's a filter on the table T1, right? So from a declarative perspective, this query looks like this, right? You have scans at the end, the leaf nodes here, and then the scan of the 2 source tables, the T1 and the T2, and then you do the join, and then you do this filter, right? This is a declarative way, but that's not the most efficient way, right? You want to apply the filter before you do the join, because if you apply this filter on T1 before you do the join operation, which is a very expensive operation, is going to deal with much less data, right? So here, if you look on the right-hand side, this is a very simple rewrite, which is called predicate pushdown. So you're pushing this filter condition right on top of the scan. So you're doing the filter on the table T1 before you do the join. So the query on the right should be done much more efficiently than the query on the left, right? So that's what's called a rewrite. Here I have a SQL equivalent, and this is a SQL equivalent to that. But rewrites in TiDB, there are so many of those. But this is one of the most common things, which is called the predicate pushdown. You want to apply filters as early as possible in your processing. Okay, so back to the second piece I talked about, which is this logical planning, the enumeration. And let's take a simple example here. Let's take this example where I am joining 3 tables instead of 2. Like the previous one, I'm joining T1 and T2, and then joining with T3 on A1 equal A2, the second join on C1 equal C3. Very simple query. So there are at least 2 ways to do this query from join ordering, right? And you can see it here, right? I can join T1 and T2 first, and then with T3. This is how the original query was written, right? Or I could actually do the join between T1 and T3 first, and then join with T2, right? Both will produce the same result, and they could be a huge difference in performance between these 2. So the optimizer needs to decide which one of those to do, right? Make sense? In addition to, the next step is, so this is what's called the logical enumeration, right? Because these are still logical, right? So the physical is that how are we going to take this join to a merge join or a hash join and so on. So in a very simple way is that the optimizer will go through costing each of these alternatives and choose which one of them, right? So the costing is really the, whatever that query tree we're talking about, right? So that summation of all the nodes in that query tree. So we're talking about, the scan cost, which I call here table access method. And in TiDB also, it needs to decide if you're going to use the row store or the column store, right? So with the scan, there is also an option, number of options, and could be a huge number of options because you have indices, right? So an index is a shortcut to go and access the data itself. And as I said, this logical joins that can be physically can be a merge join, a hash join. There is an index join also. And then you pick the least one. Okay. You guys have any questions?
I have a question. So
Yeah.
TiDB has to consider the whether to use a row store or column store method. Is that a unique feature to TiDB?
Yeah, well, in any database that have both, which are not much. I mean, most databases are either an OLTP or OLAP. So there are very few database products that they have both. And that's one of the challenges actually we have in TiDB, is this dual storage system. Yeah.
Is the step to choose between a row store or a column store unique to TiDB?
Oh, okay. Thank you. I didn't quite hear it.
Yeah, that's a good question. That's actually in our team. That's one of the challenges we have, is how to choose one over the other. Okay, so back to these basic components I talked about. Okay, so query rewrite, I gave an example. Logical planning, I gave an example, and logical to physical, I also gave an example. And for the query rewrite, logical planning, this logical to physical. So what we are claiming here, that these problems have been studied very well. I mean, this subject of relational database system is over 40 years in the research community and in the database. And the earlier ones were the DB2, the Microsoft, the Teradata as well. That's my first company I worked for. So these things have been studied very well. Tons of PhD dissertations and research papers on this topic as well. Tons of patents as well on this. So these problems have been studied very well. So somebody would say, okay, well, you shouldn't have a hard time doing those, right? But really the difficult part until today is the actual costing. So this is still an ongoing problem. This is still a difficult problem even today after all these years. And people sometimes they call it like it's an art problem than science. Query optimizations for the costing piece, especially that's the unknown part or the wild card here. And we have ways to address that in TiDB. People have dealt with that, but one shortcut are hints, right? So MySQL, TiDB also, the user can give you a hint to the optimizer if it cannot find the best plan. Or after experimenting with the plan, the user says, okay, I'm going to give you a hint. Use merge join or use this join order, and so on. So most of the problems in this specific space is about finding the number of rows, the number of operations. So I mean, in a very simple way, the cost of execution of a query tree depends on the cost of the operator and how many rows that operator involved, right? What is the input to the operator? What is the output to the operator? And the cost of that operation. So you need to understand what is the cost of a join, or what's the cost of a filter, what's the cost of an aggregation, and so on. And usually with the issue with the estimation is about finding the number of rows. So the number of rows is the most challenging piece here. So here is some information about, there are a lot more than this, but I just listed some of the common ones of estimating number of operations. So we're talking about estimating the number of rows that flows into these database queries, right? We're talking about from the scans. So if you have a scan on a table, you want to estimate, and you have a filter, you want to estimate, okay, you have 1 million row going in, you want to know, is it 1,000 rows after the filter? Is it 1 row? Is it the whole, all the 1,000 rows? So some of the issues with this is still, okay, so we rely on, maybe I'm making an assumption that you guys know about statistics, so let me take a step back. So a way of actually figuring out this number of rows is by using statistics. So databases, and you probably have seen that, you could if you run analyze on MySQL, and we are familiar with analyze, right? Analyze is a common thing for collecting statistics in databases, including TiDB. So the optimizer will try to use these statistics to figure out the number of rows, right? And usually that's done for the raw data, right? For the scans. But the rest of estimation, there are several different algorithms to do that, right? So based on the row statistics, you could find what is the expected number of rows after a join or after an aggregation and so on. So some of the problems with this background on statistics is stale statistics. What does stale statistics mean? That you may collect statistics on the data now, and then you have the data will change and you don't recollect. So your statistics is out of date. Data distribution. So a lot of the models we use and this statistics estimation assumes uniform distribution, because that's your best guess. So if you have skewed data, if you have these statistics limitations, so histogram is part of the statistics. When you do analyze, you get these histograms. Okay. Filter selectivity is a common problem too. So if you're selecting from a table and you say, B1 greater than 5, how many rows is going to qualify for that condition, right? Correlation between columns. Sometimes you have multiple filters that they are related. If you say state equal California, if you say zip code equal 90278, that's my zip code, and you say state equal California. State equal California is redundant here, right? Because 90278 implies state equal California. So optimizers, database don't understand that. They don't understand this correlation between predicates and correlation between columns as well. And correlation between columns, this is something called, the most extreme was called functional dependency, right? So if you have a row that have a transaction ID, which is unique, you could derive all the other columns from that, right? Because for that transaction, you know what's the product ID, you know who's the customer, you know what's the store, and so on. So there are so many assumptions in this cost model, statistics model, that makes it hard to get accurate statistics. So solutions, and there are so many solutions. So for the stale statistics, you need to be more smart about recollecting statistics. You don't want to overdo it, right? You don't want to collect statistics every time you get one row inserted, because there is a trade-off, right? Statistics, there is a return on investment, right? It costs you resources to collect statistics, and it helps you reduce resources by having a better plan, right? And there are other ideas on making the plan stable, which is called plan management. Plan caching makes the plan stable, but also helps you with reducing the time to do the planning, which in some cases is very important. If you have a simple query that you don't want to spend time on doing the optimization and the plannings. And as I said before, it's the poor man method is hence, right? So this is the last resort people should do. And then the new area, which is in red here, that I was talking to some of you earlier, is this feedback. So this is kind of learning. It goes along with this AI and machine learning these days. And we are trying to adopt some of those also in TiDB. Is you could learn from previous execution of the same query and get feedback to improve the query execution plan for the same query when you see it again. Okay, so I talked about, everything I talked about so far is about just query optimization in general in a very high level way, right? I mentioned TiDB here and there, but was not the main focus. So let's keep also this general as well. We'll get to TiDB and how it's different. So this is So these days, the new applications that TiDB sees and TiDB, or any way for data management, is the challenges is the large data volumes and the need to scale, right? So MySQL doesn't scale, right? So that's maybe one of the motivations of people moving from MySQL to TiDB. You scale in terms of data by sharding your data, by partitioning your data. But sharding means that you have different storage, and you can add storage when you have more data, right? That's what here, scaling the data. And also we have seen a lot of, so this is on the scale of the data perspective. On scaling the application itself, I've seen many examples where you have somebody, they have this software as a service companies. They do have an application, but they want to clone the same application for different customers or something similar. So what they do, they want a fast cloning of their software as a service, and they need database that can help them with that to do this cloning quickly. So part of the application is the backend, right? So they have the backend, so they want a way to replicate the same schemas, and having in the multiple tenants there. So that's another aspect. So scaling the data, scaling the applications, and also people don't want expensive DBAs to run their system. They want database that reduce that cost and do things out of the box. So these are the key motivations for us in TiDB. Okay, so now we're talking about a bit about TiDB, keeping in mind these challenges. So for the stale statistics, for the data that grows, we have something called auto-analyze. So this auto-analyze is a smart feature that does the statistic collection in an intelligent way so that you don't overdo it or you don't underdo it, right? And we do support query caching, for the things I mentioned before. And we have something called plan management. So plan management or SQL binding. So SQL binding means that I bind a SQL to an execution plan. So the users can do that themselves, or we can do it for them in some semi-automated and hopefully in the future a full automated way. And this will help getting an execution plan during their rapid development, and then they don't have performance regressions. And for the scale of data, we, TiDB really, that's maybe the core value of TiDB from the start, is the sharding and partitioning. And there is a difference between sharding and partitioning, right? So you may apply partitioning within a shard. So sharding is physically, you have different nodes or different machines that host a portion of the data itself. And then if you're really doing a scan for a specific range of data, you don't have to go to all of them. You just go to one of them or some of them, right? And we have something also cool that we have done last year, and I was involved with that as well, is this index advisor so indices are key in OLTP systems because it's, usually your queries, you are targeting a specific row or a small number of rows. So having the right indices is key to performance. And usually it's very hard for the user. So really creating an index is it's part of your DDL, right? I mean, you guys are familiar with DDL, right? It's creating DDL, you create tables, you create indices, what have you. You create these objects. So indices is part of this schema. And it's very hard, and it's optional. You don't have to define an index, right? You could run an application with just your raw data. So indices are used for performance, and sometimes they're used for constraints, for integrity constraints, right? Because you could say, I want to define a primary key. So if you're familiar with primary keys, primary keys is what you define to enforce the uniqueness on data. So we have built a tool that really try to recommend indices for users without them worrying about this complex problem. Okay, so now we're talking about TiDB a little bit more. So this is a very high level about the TiDB architecture. The key takeaway is scale, right? And distributed. So you can see there are three key pieces here. Is the PD, the TiDB nodes. So the TiDB nodes, don't mix that with the TiDB database. It's the same name used for that component, which is I find it to be confusing, but this is the way it is. So the whole thing is TiDB, but these are also TiDB nodes. So TiKV and TiFlash. So these together is what is defined as the storage. And TiKV is the raw store, that's the primary storage. And TiFlash is the optional column store. If you want to explore the HTAP capabilities, HTAP for hybrid transaction analytical processing. That's what HTAP stands for, right? So, okay. So and the nodes above these PD nodes, they handle cluster metadata, transaction management, and that kind of stuff. The TiDB nodes, these are the ones that get the SQL, do the parsing, do the optimization. So the query optimizer is part of the TiDB node. And also it has an execution engine as well. This is where some of the joins and aggregations for the raw store happens. While TiFlash actually is more of a storage and compute. So TiFlash also has capabilities of doing joins and aggregations and stuff like that. Okay, yeah.
So you mentioned the query optimizers on the TiDB cluster.
Yeah.
Does it look at any other component in the architecture to make its optimization?
Yeah, it needs the metadata, right? Yeah, so that's, exactly. It needs the metadata, and that's what the PD will do, will, trickle down this metadata to the TiDB nodes. So you can see that, there is scaling along different fronts, right? If you have a huge number of requests, you could scale the TiDB because these are the connections you get to so that you can process the SQL. TiKV, you can add more if you have more data, right? And also TiFlash, they go hand in hand. The PD cluster also is scalable. You could add nodes there as well. If you have lots of transactions going on and things like that. Okay, all right. So we're saying that the query optimizer in TiDB is distributed aware. So it is not distributed itself. So the query optimizer run on one instance of TiDB. The processing of the optimizer is not multi-threaded. It's not distributed. There are a few companies out there that they have done the query optimizer this way, but that's a whole different topic. But TiDB optimizer is aware of your storage. It's aware of how the data is distributed because it needs to know the cost, right? In some cases also it needs to know which TiKV node to go to. Sometimes you may have a single row, then you can just go to one node and get the data. And sometimes if you have a filter, then you could know, well, I just need only node 1 and 3 instead of all the 4 nodes, right? So it is aware of that. It's aware of also the cost because it knows the distribution. And the same thing on the TiFlash side. It understands that storage system. And also knowing both systems, it knows it can tell which one to use, right? So here's a very simple query from product and sales, and the product table here. It has an index. So one option is to go on the row store And the same data on the column store, right? These are duplicates, right? So the optimizer will try to see which one is better to go after for performance. And it can theoretically mix and match. Some tables go from here, some table from there. We haven't done that in a perfect way, but in theory, and maybe in the future, we'll be able to have a nice, I mean, in the extreme cases where you have one table that fits better. I mean, right now we do that on the table level. We will be able to choose which ones, but in the compute level, what we can do in the future, we can also try to choose which of these systems to use. So back to plan management, because I mentioned this before. You know, in some of these customer environments that things are moving fast, they want a stable execution plan. And so this plan management is a way of making sure that the user can say, I want you to use this plan altogether and stick to it by doing this, this called create binding. So the binding says, I have this SQL, you can see it here in this example here. And then the using statement is another SQL with a hint, and the plan for that SQL with the hint that plan will be binded to the SQL, which is the select star from T1 here, where B equal 1, 2, 3. Okay? So this is one way to do it. Another way of doing this binding is by using previous execution, by using this plan digest. So the digest is like a hash value of the plan. So you could specify, I want to have a plan that was already captured in the past. We could do it automatically by setting some system variable in TiDB. And there is more information on this in all these documentations. So the takeaway here is that we, for this rapid applications development, we are able to clone the schema and the metadata. So you have a SaaS application, you want to deploy a clone of that application, you want to replicate the data, you replicate the schemas, we can help them to do that. But also we can help them clone the bindings. So when they have the new application, they can rest assured that the execution plans are the same. So they don't have to, collect statistics and make sure that they get the same plan. So basically, it's a predicted cloning of their application, right? So with TiDB, this is doable. And this is a recap of how TiDB helps with the today applications. So TiKV, TiFlash address this large data volumes and the scale, right? You can add more nodes to handle that. More volatile data data is moving and we are adding data. We have this smart auto-analyze I mentioned before. We're not going to ask the user to do the analyze. We're going to do it for them intelligently, considering the trade-off, right? Because, as I said before, there is a return on investment on the analyze. And for the faster applications, we do this cross-database binding. We can allow the clone to inherit the database binding I mentioned before. So these three things allows of the challenges we talked about, the application challenge, which is the fast growth of the data, the fast growth of the applications, and making sure that the applications are stable here. I have some more references, and